In this video, I will show how I implemented a 3D reconstruction from a series of 2D RGB images. This task is composed of three main parts: camera calibration, AR image tracking, and finally 3D reconstruction. First, I took pictures using my mobile device of a checkboard calibration image, optimized to be used by OpenCV's calibration functions. Then, I took a series of pictures of an object next to a marker image that I provide to my program. For camera calibration, I used OpenCV's Calibrate Camera and Get Optimal New Camera Matrix functions, which return the intrinsics, distortion, and region of interest values needed to project the image. Using these values to calibrate the image, I then use OpenCV's Detect and Compute feature, detector function, and use that as input to OpenCV's Draw Matches function. Here, I'm computing the feature matches between my marker and the images I took of the marker next to an object. Once these matches are found, I compute the homography of the photographed image to retrieve the rotation and translation matrices that warp all the images into the same coordinate space. With this, I am now able to compute image tracking. Finally, I want to construct the object next to my marker by using all the images I took. For this, I compute the same feature matches, except that this time I do it between a selected image, let's say the first one, and all the rest of the images. In order to do this, I construct a matrix where each row corresponds to one measurement of a feature from image 1 into a subsequent image, with the rotation constraint placed in the column for the feature, and the last column of the matrix represents the translation constraint. The way I construct this M matrix in code is by looping through each tracked item, which has as key its matched feature, and as value the points in the reference image and the target image. I then loop through each list of target images that point to that feature and construct the appropriate M row for it. Finally, I stack all of the rows on top of each other to construct the final M matrix. By taking the SVD of this matrix and selecting the right singular vector of it, I am then able to get the true depth of the features in the scene. With the depth of each feature, I multiply that by the feature point in image 1 and display each 3D point using a point cloud visualizer. And as you can see, there are two separate locations of 3D reconstructed object. One is the 3D object next to the image, and the other is the image. Thank you.